this was a small example. It's not always the case, but this particular example was mentioning that sometimes a circular list was better in terms of in number of comparisons that you have to do where you're searching something in the list. The question was, why is it better? Where should I look at in this part of the code? I mean, I pointed out that this inside the while conditions, that this is where you are doing the condition check for your loops, right? And then I was saying that regardless of what's happening inside, just look at this. They're actually checking two things. And current data is not equal to X. So they're actually checking two conditions, two comparisons for condition check. This one, meanwhile, they just do check a current data is not equal to X or not. So different conditions, the first condition might not need, because we are in the circular array, we may not need to check whether current is null or not, because we probably don't have any nulls in a circular linked list, right? Because we're heading back to the beginning. Most likely we will have an extra node called head. So that is the thing. I had a few questions right after the class, so I just wanted to make sure that everyone everyone at the same page. Okay? Okay. Blah 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 blah. Have you guys started take a look at? I think you guys have started reading the 6.1 and 6.4. Have you guys looked at some of the implementation details in your textbook? The figures, programs. The programs, they want you to take a look at it from the slide. Have you looked at it yet? You should, please. Again, if I ask you something like that in the exams, I don't care about the syntax too much. As long as you can present your program, your implementation details is a reasonable way, pseudocode-like, or a bit more than pseudocode-like, I'll be okay with it, okay? So, but make sure you do take a look at some of the figures and programs, especially those program examples in your textbook that I specify in the slide. Are we clear? Okay, yes, no. How come we have less people today? Much less. 뭐 있어? 오늘? At this point, there will be less people. At the point where I call the attendance is full. Towards the end of class, I don't see any empty seats. That's a very strange coincidence, if I want to say. So we briefly start looking at the slide on arrays and matrix. I think this is chapter 6. No, chapter 7. Somewhere in 7. So let me just go over first few pages. Now we want to discuss the matrix, representing matrix in data structures, but our focus will be on how can we store matrix, maybe while minimizing the space complexity, and also same time, what might be the time complexity of doing something on top of matrix, what type of operations that we would take a look at, what might be the time complexity of each. So data is often available in tabular form, table form. I know many of you is taking database as well, so database table form, right? So it means the information is stored in some type of data structure that we covered in the database as well, right? So it's the basis for those all other courses that you might be taking. Tabular data is often represented in arrays. You could make a table with the linked list. I think it's probably next chapter. In terms of drawing it in the board, how can you make a matrix in linked list way using the node and pointers? just draw a graph. I don't care about what's say in the textbook. 피겨 그리면 어떻게 돼? 아이고. I don't know. If I draw, I probably draw something like this. Matrix is table, so I maybe put a pointer on the top, pointer at the bottom. My data is here. I have another node this way. Maybe I put a pointer in this way. I have another data here. Data. Pointer this way. 이렇게 하면, well, it's okay. Pointer this way. I don't know. Something like this is also possible, right? I mean, you just need to give them an extra pointer memory space so you can go to the next element. You can go to the one on the bottom. I mean, any possible design, any design is okay. It's completely up to you. I mean, if you don't want to look at this in array ways. Okay, matrix is example of tabular data is often represented in two-dimensional arrays. Two-dimensional arrays. Well, X and Y. So, matrices are normally indexed beginning at 1 rather than 0. So when you're actually doing the implementations, just need to be careful that your actual index starting from 0. So you usually do a -1 just to be safe. Otherwise, you're shifting everything in the 1. So you're referring to a wrong number in the wrong location. I mean, those are minor details that you should look out. Matrices also support operations such as add, multiply, transpose, which are not supported by C++ and 2D arrays. I mentioned this, and easy questions to be asked. What might be the time complexity of doing an add operation? If I have an add operation in list of ADTs for this matrix structure, data structure, then what might be the time complexity? What might be the time complexity of multiplication? What might be the time complexity of transpose? Transpose, what is transpose? I think you guys know, but we will have a definition later. Let's say there's no default given operation by C++. So people who want to do this matrix operations, matrix multiplication, division, 3D, 4D matrices, if you wish to have it, what kind of tools they might use? What kind of programs? Does anyone might know? I mean, there are a lot of choices you can use, but matrix operations, sometimes some people use something called MATLAB, or this is mathematical software that you can use. So they actually implement using C, so you don't have to, they already implemented the functions for multiplication much more efficient and fast ways. You could implement yourself with the C++, but I guarantee you it will be much slower than those tools. MATLAB are, and plus there are many other tools as well. So people who's interested, then you can take a look. I think even in Python, if you're using a Python, there are some libraries that actually support this type of functionalities if you use a right libraries in a way. Introduction. It is possible to reduce the time and space using customized representation of multi-dimensional array. Beginning, I said, is one of the goals of this covering this matrix is hoping that we could minimize the time, space, and time complexity if it's possible. They say customized representation. So we do something with this, where to put the numbers in, and some of the slides will show you the way of representing two-dimensional array into one-dimensional array. Instead of having big table like that, it's table, but still table, but in actual store in the memory, we could use a simple 1D array to store all the numbers. That is possible with the very simple approaches. So that's our focus in this chapter. This chapter focuses on row and column major mapping, representation of a multi-dimensional arrays. Row and column major mapping is one of the ways that we can store two-dimensional array contents into one-dimensional array. So two simple examples. Class matrix. Of course, every chapter, previous chapter linked list, list has a multiple ways of defining their own class, different implementations, whether you use array-based or linked list or indirect addressing based. So we will basically look at the class definition of matrix ADT implementations. And what are the special type of matrices? I think it's the next 4.2 slide. They have examples of different type of matrices, which you already know many of them. I mean, diagonal, tri-diagonal, triangular, symmetric, sparse. We'll take a look at it just briefly. Some of this matrix has a lot of zeros. A lot of zeros in the entry. Is it a good idea to have all those zeros into our memory space? We all know it's going to be a zero all the time. So hopefully they can find a way not to store all the numbers, because those empty spots, we know that's going to be a zero. So we just store a part of the entire matrix that will be still good enough. That saves our memory space as well. So those are the basic ideas of mentioning this special type of matrices. 행렬할 때 뭐 이상한 모양들 나오는 매트릭스 그거예요. 근데 메모리에 어떻게 잘 넣을 수 있는지 나중에 나와요. Very simple representation. One dimensional array representation in C. Somewhere in the memory I allocate. How do I get that space? My array. I don't know, that's a character. So if I want a 10 character, then I allocate the arrays for 10 characters in this way, and we know where it starts. We usually call it from index 0, 1, 2, 3, 0 to 9 if it's a 10 space. 그죠? We all know this. Here is an example of one-dimensional array. Sorry. I promise I will remove this animations. I don't like this animations. One-dimensional array X, A, B, C, D map into a contiguous memory location. What is contiguous? What is contiguous? One thing to notice. Not just this course, other courses, your upper years. Some of the vocabularies that we use here, I mean, they almost similar, but they might have a slight different definition on the dictionary. Okay? So sometimes it's a bit difficult to get what it means from the English dictionary. So they have these words they use differently in different fields, okay? Just in case. Contiguous is just one of the same word, but it's contiguous. Memory location, what is contiguous? Others similar word consecutive. It's one next to the other. So address space is as a one. It's not index 1 is here, index 2 is there. It's not like that. It's consecutive memory spaces. So it's one next to the other. Why is it good? We will take a look at it more carefully for if you guys take the operating system courses later when you're covering the memory management for contiguous memories and other type of designing. And here it says array. When I specify the array, this portion, no gaps between, will be given to this variables. Location x1 is start plus I. I mean, if start location of the address is 10, then next one is 11, 12, 13. That's how you get the indexes. Very simple representation. Space overhead. 큰일 났다. Space overhead. Memory. Like that. Space overhead 4 bytes for a start. Character 4 bytes takes to store 4 bytes. So another 4 bytes, 4 bytes. So in case of character, 여기 캐릭터가 1바이트인데. Let's change to integer. It's okay. Exclude the space needed for exclude the space needed for elements of x. Let's just forget about this and just one space for integer is 4 bytes will be good enough. And then if I need to store maybe 10 variables, then I need what? 40 bytes to store. What about 2-dimensional arrays? 2D arrays, the elements of a 2-dimensional array A declare as integer A 3x4. We all know how they look like, right? 3 rows and 4 columns. And each one have their own index. So if I wanted to take a look at the first elements in this leftmost top, index is 0, 0, 0, 0. It's like a coordinate, x 0.0. And next one, as it is, 0.1, 0.2, 0.3, in this way. This is 2-dimensional array. We already know how much space that it requires for this type of integer array. We have discussed this, right, when we're discussing the space complexity. Rows in 2D array, row 0, row 1, row 2. We all know this. Even more. I can't believe I put an animation for this. I treat you guys like a kindergarten kids. Columns, we all know columns. 2D array representation in C++, 2-dimensional array X. View 2-dimensional array as one array of rows. So there might be a way to take a look at it as this one is another array, 1-dimensional array, the single row. This one, separate array. This one, separate array. That's actually what's being done in C++. So there is array X. Array X has elements of another array. Okay, so it's an array of array. X is a big array having 3 elements, but elements of each element is another array. Array. So row 0 has A, B, C, D. Row 1 has E, F, G, H, I, J, K, L. That's how you represent a 2-dimensional array in C++ or C. It doesn't really matter. So it kind of makes sense, right? Kind of makes sense. Store as a 4 1D array. So I need 4 1D array to store this in 2-dimensional array. Why 4 again? 왜 4개야? X has 1, and each row is also 1. I have 3 rows. I need index of those rows, so 4. Space overhead for 4 1D arrays. 4 separate 1-dimensional array linked in that way. 못 해먹겠다 나 이거. 에휴, 아니다. 너무 안 보이지 이러면. 이렇게 하면 좀 이상하니? 안 보이니? 야, 보이지? 우리 이렇게 합시다. 내가 못 해먹겠다 이렇게 하니까. 장님으로 수업하는 것 같아. 하나도 안 보여. 미안. Space overhead for one-dimensional array, 4 by 4 bytes, 16 bytes. So think of it as having a one head point for the array. Declaring one-dimensional array takes 4 bytes. You need 4, so 4 by 4, 16 bytes. It's required for representing a two-dimensional array. Okay, number of rows plus 1 because I need 1 having an index to 3 of the others. Hopefully you get the ideas for this. So again, like I say, it's an array of arrays. Array having its elements as also another array. Requires contiguous memory of size of what? What is the size of X? 3. I have 3 rows. Right? The rest of the arrays, I have a size of column 4. So 3, 4, 4, 4. So one memory block size is number of rows, and number of rows block size of a number of columns. That's simply what it means. Forget about all this. Draw this. You know how much space or how they actually look like in C++ representations. Or C, it doesn't really matter. Easy. What is row major mapping? What is row major mapping? In this way, it's a 3 by 4 array converting into one-dimensional array of Y, collecting elements by rows. I just remember. Example 3 by 4 arrays converting into one. The overall goal of this mapping strategy, mapping is allocating each element into somewhere. Row major mapping is the way of putting this two-dimensional array into one-dimensional array. How? Converting into 1D array Y by collecting elements by rows. Very easy, by rows. Within a row of elements are collected from left to right. Rows are collected from top to bottom. A, B, C, D. So I start writing A, B, C, D, E, F, G, H, I, J, K, L, M. So index point 0, 1, 2, 3, 4. Fifth element, 5, 6. This way. Ta-da. What do you need to have? What do you need to have? Maybe I need some kind of formula to find where things are later. Usually questions will be asked, what is in the position 0.1 in this two-dimensional array? 0.1 should be B. Okay. But first row is quite easy. I mean, it's 1. We can find out. What if you start going into second row? Very simple formula. Maybe you times by 4. First row takes 4 elements. 4 times row number plus whatever index that you have. Then it will get you the place of the elements that you wanted to take a look. Very simple approaches. Loading element xij. This is just what I just described. Give me an element at position I and j. Very simple formula. It doesn't need to even look at what's in the above. I times c plus j is giving me a position of the elements that I'm looking for. Assume x has r rows and c columns. Each row has a c elements, I rows, and to the left of I row. So I times c elements to the left of x, I, and 0. X, I, and j is mapped. Mapping function will give me, using I and j, will give me the actual location in one-dimensional array. That's my mapping function for this one-dimensional array. I times c plus j. without even looking at the next slide, what might be the column major ordering? This one, we take a look at left to right, top to bottom, column major ordering. How do you store into one-dimensional array? Yeah, top to bottom, left to right. This way, columns first. This is nice. This is working because we have a complete matrix. No changes of the element size and stuff. Space overhead, 4 bytes of start of one-dimensional array, 4 bytes for C, number of columns. So it's 8 bytes. So it'll be slightly less than the previous space overhead for 16 bytes. Space overhead for declaring this one-dimensional array. Note that we need a contiguous memory size of RC. Why RC? We need to store that many elements into one dimension. 이만큼은 다 있어야 될 거 아니야. 개수만큼은 다 있어야 될 거 아니야. 공간이. Okay. Like you guys know already, column major mapping. I don't even need to look at it. This way. 그죠? A, E, I, B, F, G, J, C, G, K, D, H, L. Converting one-dimensional array Y, collecting elements by columns within a column of elements are 뭐라 그러는 거야? Within a column elements are collected from top to bottom. Columns are collected from left to right. We get that. Row major, column major, so easy. Nothing is interesting in here. Hopefully we can increase the maybe dimension of the matrix that we're working with. Can you do this for 3-dimensional array? Can you still use one-dimensional array to represent a 3D matrix? 그죠? But you might have a different formula for that too. Okay, why we do this? As you can see, the space overhead to having this array is less than having a 2-dimensional declaration for arrays. So we reduce the space complexity a little bit. Row, major, column mapping to the array 3, 6 is a simple example, and this is a comparison of the two. We know from the previous examples. There are a bit more explanation in your textbooks, so start reading the figures there, but this part, there's nothing to read. I mean, as long as you're awake in the class, nothing to read. It's actually most of the examples that I ask you to read in the slide, you probably doesn't take that much time to read it because I probably mentioned at least one or twice. So as you're afraid of reading English, but I'm pretty sure it would take much less time than you are thinking. 아마 내가 매번 수업 시간마다 읽어 그래가지고 매번 이걸 언제 다 읽지? 지금도 챕터 7까지만 하면 이만큼이 잡히잖아 손으로. 그죠? 괜히 쫄아가지고. 근데 내용이 어려운 건 아니고 또 한 번 여기서 얘기를 했기 때문에 실제로 이렇게 읽으려고 보면 아는 얘기라 시간이 생각만큼 오래 걸리진 않아요. 꼭 책 안 읽은 사람들이 책 읽을 거 많아요 이래가지고 지레 겁먹고 안 읽고 그러지. 생각보다 읽을 게 많이 없다니까. If you take a look at your books, they nicely explains for mapping functions for 2D array. They just simply replace the declaration into the size of the array declaration into U1, U2, and you can actually, it's the same formula that you use. They actually also give a 3-dimensional array representations. I think they do it this way. Array A, declare in U1, U2. If you want to take a look at array element in I and J position, that's the formula to use to compute the location of a elements that you're looking for. Likewise for 3-dimensional arrays. nice short explanation on your textbook as well. I mean, if you think about it, it's pretty obvious. 3dimension도 똑같아요. 로가 2개가 늘어나니까 계속 내려가서 이쪽도 가고 더해서 가고 똑같아요. Typical exam questions. I give you a one example of maybe 3D, maybe even 4D, maybe three-dimensional matrices, but somewhere in the matrix is a bit broken. So you might need to add extra values to get the position of a certain variables. So I might ask you to mapping function of a certain array if you want to implement that in one-dimensional array. That is very easy and typical questions I might be able to ask. I said it, so high chance that I will ask. What is a mapping function of figure 7.2a? I looked at it. It's another example like the slide that we had. Column major ordering mapping functions. I mean, what can be so different? I mean, just change the position of these variables should be fine. So do take a look at the examples on your books one more time. Maybe you might want to write it down once. Actually do one mapping for testing. They have a big matrix and they give you a formula and then maybe you plug in numbers to find out whether the formula actually works. It might be good enough for your preparations. What about irregular 2D arrays? Now the array size is not consistent. I mean, this is also possible. Maybe if you look at this as an array, just look at this part. This is my matrix. Maybe in upper part of this, it's all 0. Maybe. I only have elements on this side. So along the diagonal, maybe this part is 0. I could store 0, 1, 0, 0, 0, 2, 3, 0, 0, 0. I could do that too, but why are you wasting your space? Right? If something above this side is 0, and if you want to take a look at if someone is asking that index number for that particular location, I don't even have to look at the array. I could just simply return 0, right? That saves the time and memory. So a case like that is also possible. So this is one of the examples for irregular 2D arrays. I can define this. Irregular 2D array, ranks of the row not required to be same. It's not a complete matrix. It's a variation of a matrix. Creating and using irregular 2D arrays. Let's see. Declare two-dimensional array variables and allocate the desired number of rows. So you're actually creating a pointer to it. So you create you can interpret this code as this way. I declare index array right here. Contents, it's not 100% same, but contents of the array may be a pointer. At this pointer, it's pointing to a single array that I created. So every time it goes through the for loop, I'm pointing to the array somewhere here to the array like this. Next one is I need 3 position for that. Maybe it's somewhere in the memory like this. Right. You can interpret this as this way. So we have all different element numbers for each index that we have. So if I take a look for until you reach the number of rows, every time you reach the number of rows, you create something new. Integer array, length I. This length keep increasing. No, 1, 2, 3, 4. And then you put something in wherever you want it to. And you keep doing this as we increase the I. It goes 1, 2, 3, 4. So create new pointer, create new pointer, create new pointer. Okay? So I can keep track of the irregular two-dimensional arrays this way. When I say create, what is so important about after you use your data structure? You need to delete it for sure, okay? You need to delete it for sure. Not just this example. Other examples that we have looked at, especially for linked list examples, you create a node. Make sure you delete the node at the end. Those destroyer, the ADT functions have this in it, destroyer functions. Okay? Make sure you've done that. Matrices, again, M by M matrices is a table with the M rows and N columns. Mij denotes the elements in row I and column J, common matrix operations, transpose, addition, multiplication. What is transpose? 니네 행렬 어디서 배우니? Where'd you guys learn 행렬? 아무도 안 들려. 뭐라고? 아, 고등학교 때. Okay. Then you probably already cover it. 이거 뭐라고 써? Matrix A transpose of A. 그죠? You switch the location of A elements in the single matrix. Addition, don't make me do this addition. You all know what it is. Transfer, so, 이거 몰라? A transpose 이렇게 쓰잖아. 이게 뭐예요? 여기 있어요. 깜짝이야. 그럼 어떻게 써? transpose를. Multiplications, I don't need to explain, but only thing that I remember from multiplication is if I do a n by n matrix multiplied by n by q, then I will have n by q matrix for the result. So the rows size has to be matched in the middle so I can do the multiplication of this. So product of matrix A and B is only defined when the number of columns in A equal to the number of rows in B. Let A and B n by n matrix be n by q matrix at A times B product will produce an n by n by q matrix with the following properties. Cij is what? Summation k 1 to n, k indexing 1 to n, A ik times B kj. What is that? This times this. You add those numbers. 그죠? That's summation. Summation. You take every element from this way, the other matrix in this way. They adding summation. So if you see a summation mark, if you try to code this, they usually need one for loop at least. 그죠? In this way, you might need more than that. Anyway, read 7.2. 저렇게 써놓으니까 좀 새롭지? Summation of ij plus. 이렇게 하면 뻔한 얘기인데. Read 7.2 for your high school memories. I don't care. Just to take a look. So this is how you define a matrix class. There are many possible implementations of matrix class. This is not just one. I mean, we could have this. We could have a linked list of different way of implementation. This is just one of the examples for simplifying. Use a built-in a two-dimensional array. I'm just gonna decide to a simple two-dimensional array as it is. I'm gonna call it as a matrix class. Matrix class have a rows and columns, and T pointing to a data. I mean, those are pretty much same. Shortcomings of using a two-dimensional array for a matrix. Index is off by 1. actual index in the array start from 0, but actually when we're referring, it's 1, 1, 1, 2, 1, 3. So be careful not to make a mistake when you actually do the coding. Arrays, C++ array do not support matrix operations such as add, transpose, multiply, and so on, inverse. Why do you even need to calculate the inverse with your hands? There are many good softwares that do it for you. 그냥 그런 거 받아서 써. 손으로 계산하지 말고. Anyway, have you ever had a chance to calculate matrix outside of course in your life? 거의 없죠. Suppose that x and y are 2D arrays, cannot do x plus y, blah, blah, blah. We know that. We need to develop class matrix for object-oriented support for matrix operations. Building an app, we're actually implementing ADT, matrix ADTs. See program 7.2, 7.7, read section 7.1, 7.2, but you already kind of read it if you're just sitting in this class. So not much to discuss this basic array part, matrix part. Let's move to 4.2. Now we're going to take a look at, 또 이렇게 하자. 내가 왜 이걸 애니메이션으로 넣었을까? 내가 미치지 않았을까? 이렇게 하자. 붙였다. Special matrix. A square matrix has the same number of rows and columns. We've seen a irregular matrix. They don't have the same number. 아니다. That have inconsistent number of columns. But this one, square matrix means same number of rows and columns. 3 by 3, 4 by 4. 5 by 5. Some special forms of square matrices are diagonal, tridiagonal, lower triangular, upper triangular, symmetric. And each defines in this way. Diagonal, M, Ij equal to 0. If I and j are not equal. What does that mean? Maybe it's easier to look at. Tridiagonal I and j will be equal for I. Difference between the two is less than 1. So let's wait. Diagonal I and j not equal. If it's not equal, it's all 0. Only the values will be on the diagonal. 이거 뭐야? 다이아고널 뭐라 그래? 다이아고널 뭐라 그래? 몰라. diagonal. 대각선? 아닌데. 뭐라 그러지? diagonal. Tridiagonal. The difference between I and j is less than 1, then it's all zeros. So you just calculate the index and whether they follow the same property. Lower triangular, the values will be on the lower side of the matrix. Upper side will be 0. This might be a perfect example for using that irregular matrix that we looked at for examples. So, upper triangular. This side only elements, no elements at the not true. There are elements, but those elements are all zeros. Symmetric. What is symmetric? 이게 뭐야? 이거 모르면 IQ 테스트 빵이지 뭐. If you flip it, then exact same positions will be there. Symmetric usually means 뭐 보면 되지? 미술에 보면은 뭐 있지? 데칼코마니. 그게 symmetric. What is asymmetric? They don't match. Asymmetric. We don't have asymmetric matrix here, but if you go this way, same, then symmetric. If you go this way and take the other way around, then asymmetric. Those are the common terms that use in many different areas. So simple figures will representing this special type of square matrices Remember, these are square matrices, special types. Okay, it's all n by n matrices. Special matrices. Why we are interested in these special matrices? Why? Why? I mentioned it in the last slide as well. I mean, we like to minimize the memory space of storing these values. I don't want to store zeros, right? This similar idea is being used in other tools. How does a zip work? WinZip, RZip, those are compression tools, right? What are they doing? What is compression? I discussed this last year as well, right? What is compression? Exact translation might be what does it do? 맨날 쓰면서 what does it do? 줄인다고 얘기하죠. What does that mean, having a reduced size? 그게 뭐야? As simple as this. If they have many zeros in their file, I can tell, if I take out all the zeros and merge it together, later I know where those zeros are, I can bring it back. So when you actually compress the files, they remove unnecessary portion, which you can recover it later. 예를 들면 파일 집한다는 게 마이크로소프트 워드나 이런 파일들 보면 이렇게 바이너리로 쭉 찍으면 막 비어 있고 0으로 돼 있고 이런 되게 많아. 마이크로소프트 워드보다는 엑셀 같은 거 계속 반복되는 문양 이런 게 많아. 반복되는 걸 이렇게 얘는 반복되는 놈 해갖고 일단 딴 데 써놨다가 줄여. 그걸 빼고 이렇게 파일을 확 줄여. 그거 딴 사람한테 주잖아. 그럼 나중에 반복되는 놈이 뭐인지 알기 때문에 그 빈 공간에다 반복되는 놈만 이렇게 치워놓으면 다시 파일이 살아나. Compression. That is also doing what? Space complexity, right? Try to reduce the space it takes to store those files. Similar idea. We can provide more efficient implementations for specific special matrices because we know the structure of those special matrices. Then we can maybe have a bit less overhead implementations of handling those matrices. Rather than having a space complexity of order n square, why do they say order n square for space complexity? Well, because it's n by n, I need n square amount of memory in worst case. We can find the implementation for this order n. Maybe just n, linear space. Space complexity might be possible. We need to be clever about store and retrieve operation to reduce time. Again, I know where zeros are. I know the structures are. If I'm dealing with a symmetric matrices, I mean ij, ji will be same. So someone asked me what's in the element in position ij. I maybe look up the matrix. Memory lookup. Next time someone asks me what is an element in ji, I know it's the same as ij, maybe returning the same values because we're dealing with symmetric ones. Those are radical examples, but it's just one example. It's two smart store and retrieve operations. Hopefully we can remove a computation time, memory access time to be more exact. Read example 7.4, 7.5. I'm not going to read it for you. Where do you use this matrices? It's one of the examples. Where do you use this matrices? I mean, this clear. I want to get to one city to the other city. Then if I give them an index number of one city and the other city, then I can look it up. Actual distance between the two cities in this way. It's an organized way of representing it. Your navigation have this too. So, diagonal matrix naive way of representing n by n diagonal matrix is T, class T for matrix D and N, Di 1 minus I minus 1, J minus 1 for Di and J requires n squared times size of T bytes of the memory. I need a n squared memory, integer 4 bytes, n by n. So, better way, if you just look at this blue part, I just need n, because half of this may not need. Better way, TDN, Ti minus 1 for Dij, where I and j equal 0 for ij, I minus I and j not equal, requires n times size of T bytes of the memory. More details will be given diagonal matrix. I just kind of exclude from the slide because it's quite obvious, very small implementation details. Let me see. Tridiagonal. It's keep same. I mean, same example of examples. Non-zero elements lies on the 3 diagonals. Non-zero. This one is go. So if you take a look at this matrix, I only need n spots to store 2, 1, 4, 6. Rest of them 0. I don't need to store. So this one, tridiagonal matrices. Only here 0, 0, 0. A certain position is 0. Non-zero elements lies on the 3 diagonals. 1, 2, 3. So, main diagonal I equal j. Diagonal below the main diagonal I equal to j plus 1. 하나 아래 내려오니까. Diagonal above the main diagonal I equal j minus 1. So that gives us 3n minus 2 elements on these 3 diagonals. 그죠? 하나 아래. The one below takes 1 less elements than the main diagonal. One above also takes 1 less than main diagonal. 3 times n minus 2 is total number of spaces that I need to store for the elements. Okay, so I can continue on this each matrix for the next class. Let me see. How many do we have? Again, I recommend to take a look at the slide briefly because I'm going to go a bit faster. I'm going to finish up this slide next class a bit fast. Okay, just do some of the preview because it's quite obvious stuff. 이거 좀 알기 쉬운 거니까 다음 시간까지 남은 슬라이드 이렇게 한번 쓱 보고 와요. 다음 시간에 요건 좀 빨리 확 넘어갈게요. 괜히 뭐 많이 설명할 이유도 없어서. Okay, I'm gonna call your attendance. Before I do that, any questions for today? 스페셜 매트릭스를 어디다 쓰냐고? 여기서는 어디다 쓴다고 얘기하기보다는 이런 것들이 있으니까 저런 것들이 있을 경우에는 그거에 맞춰서 스페이스를 줄여가면서 프로그램을 짤 수 있다. 약간 그렇게 받아들이는 게 맞을 거예요. 그렇게 받아보면 그 하나 예제로 나온 거지. 이게 나중에 다이아고널 매트릭스가 어디 쓰냐 이렇게 딱 그렇게 얘기하기는 사실 좀 힘드네. 아까 diagonal matrix space 어떻게 줄여? How do you reduce the space for diagonal matrix? I mean, in terms of implementing this, it's simple. I only need to have 4 spots instead of having n by n and square spots. 그렇지. That's why they say n here. And if I have this implementation, someone asked me the index point for this point. Like someone asked me 이건 뭐야? 1.1. 1.1. Then I don't even need to take a look at this list. Maybe before I go into the list, this array, I made some checking point, index checking functions. If I is less than 1, equal to 1, or j is, I don't know. Also, I and j not equal to each other, then return 0. Something like this. 잠깐만, 질문이 있어서. 뭐 이렇게 하면 되잖아. 앞에다가 and then if it's not if it's outside, then I can do return something by looking at that this way. 실제로는 어레이 4개밖에 없으니까 그 바깥에 물어보는 애들은 먼저 그 전에 처리를 하는 거예요. 이렇게 되는 애들은 볼 필요도 없이 다 0이니까 0 보내고, 그거의 컨디션에 맞지 않는 애들은 실제로 어레이 4개 있는 어레이 봐서 그 맞는 포지션에 있는 거 던져줘라. 그러니까 실제로는 하려면 저거 16개가 있어야 되는데 4개만 있어도 된다. 그런 뜻으로 받아들이면 돼요. Hopefully that's good enough. Any other questions? Okay, I'm gonna call your attendance now.